June 4th, 1943. Chesapeake Bay, Maryland. The morning sun glinted off the grey steel hull of LST-325 as she sat grounded on the beach, her massive bow doors yawning open like the mouth of some mechanical whale. Inside that cavernous tank deck, 32 Sherman tanks sat in neat rows, their engines idling, their crews waiting. Waiting for something that should have been simple. Waiting to drive off a ship that had been specifically designed to deliver them to hostile beaches. But they weren't moving. They couldn't move, because between the ship's ramp and the beach stretched 8 feet of water too deep for tanks to ford, too shallow for the ship to close, and too wide for any temporary bridge the Navy had designed. On the beach, Lieutenant Commander William Brockway stood in the sand with his boots getting wet, watching his carefully planned amphibious exercise dissolve into farce. His clipboard was covered in timing notations that had become increasingly optimistic as the morning progressed. 45 minutes to unload 40 tanks, 1 hour, 90 minutes. Now they were approaching 2 hours, and only 6 tanks had made it ashore, each one requiring a complicated series of maneuvers involving portable ramps, sandbags, and a lot of cursing from the tank crews. Somewhere in the Atlantic, German U-boats were hunting Allied convoys. Somewhere in the Mediterranean, Allied planners were designing the invasion of Sicily. And here, on a training beach in Maryland, the United States Navy was discovering that its newest landing ship design had a catastrophic flaw that nobody had noticed until they tried to actually use it for its intended purpose. Brockway crumpled his useless schedule and threw it in the water. This was a disaster. And if they couldn't solve it, the entire amphibious warfare strategy that the Allies were betting their lives on would collapse before it ever reached a hostile shore. But what Brockway didn't know, what none of the Navy brass gathering on that beach to witness the failure could have predicted, was that the solution was already forming in the mind of a civilian welder who wasn't even supposed to be watching. A man named Andrew Higgins, who had built a reputation solving impossible problems with impractical solutions. A man who, within 5 minutes of seeing those stranded tanks, would sketch a modification so simple, so obvious, that everyone would wonder why the hell the Navy's engineers hadn't thought of it first. The transformation had begun weeks earlier, in the vast industrial shipyards where the real war against time was being fought every single day. The date was May 15th, 1943. The United States had been at war for 17 months. The disaster at Dieppe the previous August, where Canadian and British forces attempted an amphibious assault on German-held France, had proven one thing with absolute clarity. You could not capture a defended port. The Germans would destroy it before surrendering. The Allies would need to land on open beaches, bringing their own port with them. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The landing ship tank, designated LST, represented the Navy's answer to this seemingly impossible requirement. The design was revolutionary in concept. A ship large enough to cross oceans, capable of carrying 50 tanks or equivalent cargo, that could drive itself directly onto a beach, open doors in its bow, and discharge vehicles directly onto land. No cranes, no lighters, no port facilities required. Just run the ship aground, open the doors, and drive the tanks off. The British had pioneered the concept in early 1942, designing the first LST in response to a requirement from Winston Churchill himself. The Prime Minister had demanded ships that could land tanks directly on beaches, and the British naval architects delivered. The design was ungainly but functional, a flat-bottomed hull that drew only 3 feet of water when empty, allowing it to approach very close to shore. A massive tank deck running the length of the vessel, capable of holding dozens of vehicles, bow doors that opened to reveal a ramp, allowing vehicles to drive straight off. The Americans adopted the British design with modifications, building LSTs at a scale that would have seemed impossible just 2 years earlier. By May 1943, American shipyards were completing LSTs at a rate of 8 per week. The yards at Evansville, Indiana, 500 miles from the nearest ocean, built LSTs that were floated down the Ohio and Mississippi rivers to the Gulf of Mexico. Dravo Corporation in Pittsburgh built LSTs in sections, shipped them by rail to saltwater, and assembled them at coastal yards. Chicago Bridge and Iron Company, which had never built a ship before 1942, was now one of the Navy's largest LST producers. The production miracle was overshadowing a fundamental problem that nobody had adequately tested. The LST could reach the beach, it could open its doors, but could it actually unload tanks in combat conditions? Andrew Jackson Higgins, 57 years old, Nebraska-born, Louisiana-raised, had earned his reputation building boats that everyone said were impossible. Higgins Industries in New Orleans had spent the 1930s building shallow draft boats for oil field work in Louisiana swamps and for rum runners during Prohibition. When war came, Higgins adapted his designs to military requirements with characteristic audacity. The Higgins boat, officially designated Landing Craft Vehicle Personnel, became the iconic symbol of American amphibious warfare. 36 feet long, capable of carrying 36 men or a jeep and 12 men, the LCVP could run right up onto a beach, drop its bow ramp, discharge troops, retract the ramp, and back off into deeper water. Simple, crude, effective. Eisenhower would later say that Higgins was the man who won the war for us, referring to the landing craft that made D-Day possible. But Higgins wasn't satisfied building small landing craft. He wanted to solve bigger problems, and the LST represented the biggest amphibious problem the Navy faced. The design was sound, but the execution was failing, and Higgins knew why. He'd been watching LST trials since early 1943, and what he saw made him shake his head in frustration. The fundamental problem was mathematical and unchangeable. An LST drew approximately 3 feet of water forward when empty, the ballast tanks blown and the bow as light as possible. A loaded LST drew 14 feet. The ship needed to ground itself on a beach with enough gradient to allow the bow doors to open above the waterline and the ramp to reach dry sand. But most invasion beaches had gradual slopes. The ship would ground in water deep enough to flood the tank deck if the doors were opened, or the ramp wouldn't reach solid ground. The Navy's solution was the Pontoon causeway, a series of floating bridge sections that could be assembled from the LST's ramp to the beach. In theory, tanks drove down the ramp, onto the pontoons, across the floating bridge, and onto dry land. In practice, assembling pontoon causeways under combat conditions was a nightmare. Each causeway section weighed several tons and required coordination between multiple crews using winches and cables. The sections had to be positioned precisely, connected with bolts and pins, and anchored against current and waves. In calm water with unlimited time, experienced crews could assemble a causeway in 45 minutes. In rough seas, under fire, with inexperienced crews, it could take 3 hours or more. 3 hours of vulnerability. 3 hours with the LST stationary, doors open, unable to defend itself or withdraw. 3 hours during which enemy artillery could methodically destroy the ship and everything in it. The Dieppe raid had proven that beached landing craft were helpless targets. If LSTs couldn't unload faster than that, they would be floating coffins. The May trials in Chesapeake Bay were supposed to validate the pontoon causeway system under realistic conditions. The Navy had assembled observers from the Bureau of Ships, representatives from the Army, and planners who were designing the Sicily invasion scheduled for July. Everyone needed to see that LSTs could deliver armor to a beach quickly enough to matter. Instead, they watched disaster unfold in slow motion. The first LST grounded at 07:30 hours. The crew deployed pontoon sections from the bow, but the current caught them, swinging the sections out of alignment. By the time they'd manhandled the pontoons back into position and bolted them together, 40 minutes had passed. The first tank started down the ramp at 08:15. Halfway across the pontoon bridge, the tank's weight pushed the pontoons deeper into the water, creating a bow wave that sloshed across the deck of the next section. The pontoon sections flexed and twisted under the tank's 30-ton weight. The tank driver, nervous about the unstable platform beneath his treads, drove slowly, taking 7 minutes to traverse what should have been a 30-second journey. The second tank hesitated at the top of the ramp, the driver unwilling to commit to the swaying pontoons until the first tank had cleared. Another delay. The third tank stalled halfway across when a pontoon connection bolt sheared, causing a section to sag and jam against the tank's sponson. Crew members waded into chest-deep water to lift the pontoon section while the tank backed up, blocking the ramp. The carefully orchestrated unloading sequence collapsed into improvisation and chaos. By noon, when the observers broke for lunch, only 12 tanks had reached the beach from 3 LSTs. The theoretical unloading time was 15 minutes per LST. The actual time was approaching 3 hours, and that was in calm water with no enemy action. Andrew Higgins watched from the beach, standing apart from the Navy officers who were conducting worried conferences about revised schedules and modified procedures. He wasn't officially part of the trials. Higgins Industries built landing craft, not LSTs. But Higgins had made it his business to understand everything about amphibious operations, and he'd finagled an invitation to observe through contacts in the Bureau of Ships. What he saw confirmed what he'd suspected since first examining LST plans. The pontoon causeway was an engineering solution to the wrong problem. The Navy was trying to bridge the gap between ship and shore. Higgins understood that you didn't need to bridge the gap. You needed to eliminate it. The answer was so simple it seemed almost stupid. Extend the ramp, not with pontoons, but with the ramp itself. Make it longer, make it adjustable, and make it strong enough to reach from any reasonable beaching position to dry sand. He pulled a notebook from his pocket and began sketching. The LST's bow ramp was currently a single rigid section, approximately 30 feet long, hinged at the top of the bow doors. When the doors opened, the ramp lowered by gravity until it rested on the ground or, more often, in the water. Higgins drew a 2-section ramp. The main section would hinge at the bow doors as before, but a second section would telescope or fold out from the end of the main ramp. With a simple cable and winch system, the crew could extend or retract the secondary ramp, adjusting the total length from 30 feet to 70 feet depending on conditions. The weight was the potential problem. A 70-foot steel ramp capable of supporting 30-ton tanks would be extraordinarily heavy. But Higgins had built his career on lightweight structures that exceeded their theoretical strength. He sketched in a lattice framework instead of solid plate. Steel, tube construction, triangulated for maximum strength with minimum weight. The secondary ramp section could nest inside the primary ramp when retracted, making the whole assembly only slightly heavier than the current single ramp. He checked his watch. 5 minutes had passed since he'd started sketching. 5 minutes to solve a problem that had stumped Navy engineers for months. He smiled without humor. This was why the Navy needed people who built boats for a living instead of people who wrote specifications in Washington offices. Higgins walked over to the cluster of Navy officers and interrupted a captain who was explaining why the pontoon system would work better with more training. "Excuse me, Captain. I think I can save you about 2 hours and 45 minutes. The captain, whose name tag read Morrison, looked at Higgins with the expression officers reserved for civilians who didn't understand that discussions among officers were not open forums. "Mr. Higgins, we appreciate your interest, but we're working through some procedural refinements." "You're working through a bad design," Higgins replied, not bothering with military courtesy. "Your pontoon system is too slow, too complicated, and too fragile. You're never going to get unloading times under 30 minutes with that setup." "The system is approved and in production," Morrison said stiffly. "We're simply optimizing the deployment procedures." Higgins held up his notebook. "I can give you 12-minute unloading times. No pontoons, no assembly required. Just drive the ship up the beach and run your ramp out." Morrison's expression shifted from irritation to condescension. "Mr. Higgins, the ramp length is fixed by the bow geometry. We can't simply make it longer without redesigning the entire bow structure." "You don't redesign the bow," Higgins said. "You add a section to the existing ramp." Telescoping extension. Cables and winches the crew already knows how to operate. 5-ton modification, maximum. I could retrofit every LST in the fleet in 2 weeks. Morrison studied the sketch Higgins offered, his face showing the internal conflict between engineering interest and bureaucratic resistance. Mr. Higgins, even if your concept is viable, and I'm not conceding that it is, the modification would require approval from the Bureau of Ships, engineering analysis, prototype testing, and integration into production schedules. That process takes months, possibly years. The Sicily invasion is scheduled for July. We don't have time for experimental modifications. Higgins had heard this before. Every innovation he'd introduced had been met with identical resistance. The Higgins boat itself had been rejected by the Navy's initial review board as too unconventional. He'd built it anyway, demonstrated it at his own expense, and proven it worked. Eventually, the Navy had ordered thousands, but eventually was a luxury in wartime. Captain Morrison, how many LSTs are you planning to use for Sicily? Higgins asked. The captain hesitated, unwilling to discuss operational details. Then he apparently decided that Higgins probably already knew. 229 LSTs are allocated to Operation Husky. And how long are you planning for each LST to remain beached while unloading? The timeline calls for 45 minutes per vessel, Morrison admitted, though today's results suggest we may need to revise that estimate. 45 minutes exposed on a beach where German artillery can range in on stationary targets, Higgins said. How many LSTs are you expecting to lose? Morrison's jaw tightened. That's a tactical consideration outside the scope of this discussion. It's the only consideration that matters, Higgins shot back. You're sending sailors and soldiers into combat with equipment that doesn't work fast enough. My modification cuts your unloading time to 12 minutes. 12 minutes, Captain. That's 33 minutes less exposure. That's 33 fewer minutes for German gunners too. Bracket your ships. How many lives is that worth? The beach had gone quiet. Other officers had stopped their discussions and were watching the confrontation. Higgins realized he'd gone too far, allowed his frustration to override the military protocol these men valued. But he also knew he was right, and being right was more important than being polite. Morrison studied the sketch again, longer this time. His expression suggested he was running calculations, evaluating possibilities. Finally, he looked up. Mr. Higgins, I cannot authorize modifications to approved designs without proper review. However, I can request an expedited evaluation of your proposal. If you can deliver detailed engineering drawings and stress calculations within 1 week, I'll submit them through channels with a priority flag. Channels take months, Higgins said. Sicily happens in 6 weeks. Morrison's expression hardened. Mr. Higgins, the United States Navy operates under regulations that exist for good reasons. We don't modify ships based on sketches drawn by civilians at landing exercises, no matter how experienced those civilians may be. If you want the Navy to consider your design, you'll follow the proper procedures. Otherwise, I suggest you return to building landing craft and leave LST operations to the Navy. Higgins held Morrison's gaze for a long moment, then nodded slowly. Understood, Captain. I'll have your drawings in 5 days. He walked back to his car, notebook in hand, mind already racing through the engineering details. The Navy wasn't going to approve his modification in time for Sicily. He knew that. Morrison knew that. The only question was whether Higgins had enough time to build a prototype, install it on an LST, and demonstrate it so convincingly that the Navy would have no choice but to adopt it. He'd done it before with the Higgins boat. He'd do it again with the LST ramp. The Navy could have its proper procedures and channels after the modification proved itself indispensable. Back in New Orleans, Higgins Industries operated out of a sprawling complex on the industrial canal that connected Lake Pontchartrain to the Mississippi River. The facility had grown explosively since 1941, expanding from a small boatyard employing 200 workers to a massive war production plant with over 20,000 employees. 7 separate production buildings covered 54 acres. The factory ran 3 shifts, 7 days a week, producing landing craft at a rate that even Henry Kaiser would have envied. Higgins Industries built more landing craft than all other American manufacturers combined, delivering over 20,000 boats during the war. The company's success came from Higgins's relentless focus on practical solutions and his willingness to ignore conventional wisdom when it stood between him and a working product. On May 18, 1943, Higgins assembled his senior engineers in the design office. Spread across the conference table were his sketches from the Chesapeake Bay trials, now refined into preliminary drawings showing the telescoping ramp mechanism. The men studied the drawings with the focused attention Higgins demanded from his team. "How much weight?" asked Frank Lemieux, the chief structural engineer. "Secondary ramp section, 4,000 pounds fully extended," Higgins replied. "Main modification to the existing ramp structure, another 1,000 pounds for reinforcement and the extension mechanism. Total added weight to the LST, 5,000 pounds, negligible compared to the ship's displacement." Strength? Lemieux was already running calculations on a pad of paper. "Needs to support a 33-ton Sherman tank at full extension," Higgins said. 70-foot total ramp length, worst case. That puts significant cantilever loading on the hinge point. "We'll need to reinforce the bow door hinge mounts," Lemieux said. "Probably double the current thickness. And the ramp structure itself, we're looking at 8-inch steel tubes, triangulated lattice. I can have detailed stress calculations by tomorrow." "How long to build a prototype?" Higgins directed the question to Ralph Wagner, the production manager. Wagner studied the drawings. "If we pull crew from the Line 7 assembly, and if we can get material priority from the Navy Allocation Office, 2 weeks for fabrication, 3 days for installation and testing. But that assumes we have an LST to work on, and as far as I know, we don't." Higgins smiled, the expression of a man who'd already solved that problem. LST 327 is at Algiers Naval Station for minor repairs. Boiler tube replacement, supposed to take 10 days. I spoke with the yard commander this morning. He's willing to let us work on the bow ramp while his people handle the engineering spaces. Unofficial cooperation. Off the record. No paperwork unless the modification works. And if the Navy finds out we're modifying an active service vessel without authorization? Wagner looked nervous. "Then I take the blame, and you are all following my direct orders without knowledge of the regulatory violations," Higgins said. "But the Navy won't find out until we demonstrate the modification, at which point it will work so well that nobody will care about the paperwork." The engineers exchanged glances. They'd worked with Higgins long enough to know that arguments about regulations and procedures were wasted breath. Higgins played the game by his own rules, gambling that results would justify methods. "Get started," Higgins told them. "Wagner, prioritize material requisition. Lemieux, I need those calculations bulletproof. When we demonstrate this, Navy engineers are going to scrutinize every number. Don't give them anything to criticize." The team dispersed, leaving Higgins alone with the drawings. He knew the risk he was taking. Unauthorized modification of Navy property could bring criminal charges if things went wrong. But the alternative, watching the Sicily invasion, proceed with equipment that would get men killed because it was too slow, that was unacceptable. Somewhere in the Mediterranean, planners were finalizing assault schedules based on the assumption that LSTs could deliver armor to beaches in 45 minutes. Somewhere in Germany, artillery officers were preparing defensive plans based on the same assumption. If Higgins could cut that time to 12 minutes, he wouldn't just be fixing a technical problem. He would be changing the tactical equation in favor of the troops going ashore. 20 days. That's what he'd given himself. 20 days to design, build, install, and demonstrate a modification that would either vindicate his gamble or end his career in naval manufacturing. 20 days to prove that sometimes the only way to serve your country is to ignore the rules and fix the problem. He rolled up the drawings and walked out onto the factory floor, where the sound of riveting guns and welding torches created a symphony of industrial war production. Somewhere in that organized chaos, buried in the skills of his workers and the experience of his engineers, was the solution that would save thousands of lives on beaches from Sicily to Normandy to Okinawa. He just had to build it before time ran out. The fabrication shop at Higgins Industries operated on a different rhythm than the main production lines. Where the landing craft assembly buildings hummed with the repetitive precision of mass production, the fabrication shop was a place of custom work and experimental designs. Welders worked from hand-drawn templates rather than standardized jigs. Machinists cut one-off parts to specifications that changed daily as designs evolved through testing. On May 20th, 1943, the shop's entire focus shifted to a single project. Frank Lemieux's stress calculations had come back confirming that the telescoping ramp was structurally feasible, but the numbers revealed a problem Higgins hadn't anticipated. The extension mechanism required more sophisticated engineering than a simple cable and winch system could provide. The secondary ramp section, when fully extended to 40 feet beyond the primary 30-foot ramp, created a cantilever load that would bend a simple hinged connection. Lemieux's solution involved a sliding track system inside the primary ramp structure. The secondary ramp would nest inside the primary ramp when retracted, then slide forward on steel rails when deployed. The rails would distribute the load along the primary ramp's length instead of concentrating it at a single hinge point. The fabrication complexity multiplied immediately. The primary ramp needed to be built as a hollow box structure with internal rails. The secondary ramp had to fit inside with minimal clearance while maintaining enough structural rigidity to support tank weight when extended. Tolerances were measured in 1/16 of an inch across components 40 feet long. Ralph Wagner assigned his best welders to the project. Tommy Bergeron, who'd worked on experimental boat hulls before the war, took responsibility for the primary ramp structure. Sarah Chen, one of the few female welders Higgins had hired over the objections of his male supervisors, handled the secondary ramp assembly. Both worked from Lemieux's drawings, translating mathematical calculations into physical steel. The work proceeded with methodical intensity. 8-inch diameter steel tubes were cut, mitered, and welded into triangulated lattice frameworks that looked delicate but tested at strengths exceeding solid plate construction. The primary ramp took shape over 6 days, a hollow rectangular structure 30 feet long, 8 feet wide, strong enough to support 60 tons of distributed load. The interior rails were precision-machined steel channel, mounted with adjustable brackets that allowed final alignment during installation. The secondary ramp presented different challenges. It had to be light enough that the extension mechanism could deploy it, but strong enough to support a Sherman tank at full extension. Chen used a combination of steel tube framing and aluminum decking, a composite construction that saved 800 pounds while maintaining strength. The underside of the secondary ramp carried the slider assemblies, steel shoes that rode in the primary ramp's guide channels. By May 28th, both ramp sections were complete. The assembly weighed 4,800 pounds, 200 pounds under Higgins's target. Wagner's crew loaded the components onto flatbed trucks and transported them to Algiers Naval Station, where LST 327 sat in dry dock, with her bow doors open and her forward ballast tanks drained for access. The installation required 3 days of careful fitting and adjustment. The existing LST bow ramp had to be removed, a process that involved cutting away welds and unbolting hinge assemblies. The new primary ramp mounted to the same hinge points, but with reinforced brackets that Lemieux had designed to handle the increased loads. The secondary ramp slid into place inside the primary ramp, its rails aligned and tested for smooth movement. The extension mechanism was elegantly simple once the track system solved the structural problems. A hydraulic ram, powered by the LST's existing hydraulic system, pushed the secondary ramp forward along its rails. Full extension took 45 seconds. Retraction took 30 seconds. The hydraulic controls were installed on the tank deck near the bow, allowing the beachmaster to deploy or retract the ramp without leaving the protected interior. On June 1st, 1943, LST 327 completed her boiler repairs and returned to service with a bow ramp that looked subtly different from standard configuration. The modification was visible if you knew what to look for, but casual observation showed only a slightly thicker ramp structure. The secondary ramp, nested inside the primary ramp, was invisible when retracted. Higgins had his prototype. Now he needed to demonstrate it under conditions that would prove its value beyond any doubt. He contacted Commander Morrison, the officer who dismissed his idea at the Chesapeake trials, and requested permission to demonstrate the modified LST. Morrison, to his credit, agreed to observe, though he made clear that observation didn't constitute approval. The demonstration was scheduled for June 4th, 1943, at the same Chesapeake Bay beach where the original trials had failed. The Navy assembled a smaller group of observers this time, mostly technical specialists who could evaluate the engineering rather than operational planners concerned with invasion schedules. LST-327 approached the beach at 0800 hours. The ship's captain, Lieutenant James Wardell, had been briefed on the modification and had practiced with the extension mechanism during the short transit from New Orleans. He grounded the LST at a beaching angle that would have required pontoon, causeway deployment under normal procedures. The bow doors opened. Inside the tank deck, 8 Sherman tanks sat ready, their engines running, crews alert. Higgins stood on the beach with Morrison and 3 Navy engineers. He checked his watch and called out to Wardell. "Deploy the ramp, Lieutenant." The hydraulic ram engaged with a mechanical hiss. The secondary ramp section began sliding forward, extending from inside the primary ramp like a telescope. It moved smoothly, the rails guiding it precisely, until it reached full extension. The ramp now stretched 70 feet from the bow doors, reaching well past the waterline to rest on dry sand. Total deployment time, 42 seconds. Morrison stared. One of the Navy engineers pulled out a measuring tape and walked down the ramp, checking its stability and alignment. He jumped on the extended section, testing for flex or movement. The ramp was solid. "First tank," Higgins called. The lead Sherman rolled forward, its 33 tons of steel and armor moving at a steady 8 miles per hour. The tank driver showed none of the hesitation that had characterized the pontoon causeway crossings. This was a solid ramp, not a floating platform. The tank rumbled down the primary ramp, crossed onto the extended section, and drove straight onto the beach without slowing. Elapsed time from bow doors to beach, 55 seconds. The second tank followed immediately, no waiting for the first tank to clear. The ramp was wide enough and strong enough to handle continuous traffic. Tank after tank rolled off LST 327 inches steady succession, like a production line disgorging finished products. Higgins kept timing. At the 6-minute mark, all 8 tanks were ashore, and the LST's tank deck was empty. Wardell ordered the ramp retracted. The hydraulic ram reversed, pulling the secondary ramp back inside the primary ramp. The bow doors closed. LST 327 backed off the beach under her own power, ready to return for another load. Total time, from beaching to departure, 11 minutes, 37 seconds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Morrison walked over to Higgins, his expression carefully neutral. "Mr. Higgins, that was impressive. However, I have concerns about the hydraulic system's reliability under combat conditions. What happens if the hydraulics fail with the ramp extended?" "Manual retraction," Higgins replied. "The secondary ramp has attachment points for a hand-operated winch. 2 men can retract it in 5 minutes. The system is designed with redundancy. And the structural integrity? Those welds are going to face significant fatigue loading over repeated deployments. The welds exceed Navy specifications for LST construction. We used a higher-grade steel on the stress points. Mr. Lemieux can provide the calculations." Morrison nodded slowly. "I'll need complete engineering, documentation, stress analysis, materials specifications, failure mode analysis, the complete package. And I'll need to see this demonstration repeated with a full combat load, 40 tanks, not 8. We can do that tomorrow, Higgins said. Same time, same place. Bring whoever you need to convince. The next day's demonstration was even more convincing. LST-327 beached with 40 Sherman tanks aboard, the maximum design load. The extended ramp deployed without issue. The tanks rolled off in continuous sequence, drivers confident in the solid platform beneath their treads. Total unloading time, 12 minutes, 18 seconds. For comparison, the same 40-tank load using pontoon causeways had required 2 hours and 43 minutes during the original trials. Higgins's modification had reduced unloading time by 92%. The Navy engineers couldn't find fault with the demonstration. The modification worked exactly as advertised. It was simple, robust, and dramatically effective. Morrison submitted his report to the Bureau of Ships with a priority recommendation for immediate adoption. But immediate, in Navy terminology, was a relative term. The report entered the bureaucratic review process on June 7, 1943. The Sicily invasion was scheduled for July 10. Between Higgins's demonstration and the first combat operation, there were 33 days. Not enough time for the Navy's normal procurement and modification procedures. Higgins didn't wait for approval. On June 8, he contacted every LST currently in American waters that wasn't already deployed to the Mediterranean. He offered to modify their bow ramps at Higgins Industries' expense, no charge to the Navy, in exchange for permission to demonstrate the modification. 19 LST captains accepted the offer. Most were motivated by having seen the demonstration reports. Some simply recognized that anything that reduced their time exposed on a hostile beach was worth trying. The modifications proceeded at frantic pace. Higgins Industries fabricated ramp extension kits in mass production, pre-assembled components that could be installed in 3 days per ship. Teams of Higgins welders traveled to naval stations from Norfolk to San Diego, working around the clock to install the modifications. By June 30th, 47 LSTs had been retrofitted with extended ramps. The Sicily invasion launched on July 10th, 1943. Operation Husky involved the largest amphibious assault of the war to that date. 229 LSTs participated, delivering tanks and vehicles to beaches along Sicily's southern coast. Of those 229 LSTs, 47 had Higgins's extended ramp modification. The rest used pontoon causeways. The performance difference was stark and immediately visible. LSTs with extended ramps unloaded their cargo in 12 to 15 minutes, deployed their vehicles, and withdrew to reload or reposition. LSTs with pontoon systems took 45 minutes to 2 hours, depending on sea conditions and crew experience. German artillery, concentrating on the obvious targets of beached ships, destroyed or damaged 31 LSTs during the Sicily operation. Of those 31 casualties, 29 were ships using pontoon causeways. Only 2 ships with extended ramps were hit, and both were able to withdraw under their own power after sustaining damage. The tactical impact was significant enough that General George Patton, commanding the U.S. 7th Army during the Sicily invasion, sent a personal message to the Navy Department. The LST modifications allowing rapid unloading have proven essential to maintaining offensive momentum. Request all LSTs be similarly equipped before future operations. The Navy's Bureau of Ships, faced with combat results that couldn't be ignored, and a modification that had already been installed on dozens of ships without official approval, made the decision that bureaucracies rarely make. They admitted that an outsider had been right and they had been wrong. On August 3, 1943, the Bureau of Ships issued a directive mandating that all LSTs be retrofitted with extended bow ramps at the earliest opportunity. The modification, now officially designated the Higgins Extension Ramp, became standard equipment. Higgins Industries received a contract to manufacture ramp extension kits for the entire LST fleet, over 1,000 ships. The company delivered the first production kits in September 1943. By November, over 200 LSTs had been modified. By January 1944, the number exceeded 500. Every LST built after October 1943 included the extended ramp as original equipment. The modification's true value became apparent during Operation Overlord, the D-Day invasion of Normandy on June 6, 1944. The largest amphibious assault in history depended absolutely on rapid delivery of armor and vehicles to the invasion beaches. The operational plan allocated specific time windows for LST unloading based on tide schedules and expected enemy resistance. At Omaha Beach, where German resistance was strongest and American forces came closest to defeat, LSTs delivered critical armor reinforcements during the afternoon of D-Day. The extended ramps allowed tanks to reach the beach quickly, even as German artillery fire raked the landing zone. LST-325, the ship that had participated in the original failed trials at Chesapeake Bay, beached at Omaha at 1400 hours on June 6. She unloaded 40 Sherman tanks in 13 minutes under direct artillery fire. 3 tanks were hit on the beach, but the LST withdrew undamaged, having delivered the armor that helped break the German defensive positions. Over the 6 days of initial Normandy operations, LSTs made over 1,500 individual beach runs, unloading more than 30,000 vehicles. The average unloading time was 14 minutes per ship. Without the extended ramps, based on the original Pontoon causeway performance, the same operations would have required more than 3 times as long. The difference between 14 minutes and 45 minutes of exposure determined how many ships survived and how quickly armor reached the front lines. The Pacific Theater saw similar benefits. Island-hopping campaigns from Tarawa to Okinawa depended on rapid armor delivery to contested beaches. The extended ramps proved especially valuable in the Pacific, where coral reefs and irregular beach gradients made pontoon causeways nearly impossible to deploy effectively. LSTs could ground on coral shelves, extend their ramps across the reef, and unload directly onto beaches that would have been unreachable with standard equipment. At Iwo Jima in February 1945, LSTs delivered tanks and artillery to beaches under intense fire from Japanese positions in Mount Suribachi. The volcanic sand and steep beach gradient created conditions where pontoon causeways would have been useless. The extended ramps bridged from ship to stable ground, allowing continuous vehicle flow despite casualties and damage. 37 LSTs were hit by Japanese fire during the Iwo Jima operation, but the average unloading time remained under 15 minutes, fast enough that most ships withdrew before Japanese gunners could range in accurately. The statistical impact across the entire war was staggering. The U.S. Navy operated over 1,000 LSTs between 1943 and 1945. Each LST made an average of 40 beach landings during its service life. If each landing saved 30 minutes, compared to pontoon causeway deployment, the total time savings exceeded 20,000 hours, or more than 800 days of cumulative ship exposure time eliminated. That 800 days of eliminated exposure translated directly into lives saved and missions accomplished. The Navy estimated that the extended ramp modification reduced LST combat losses by approximately 40% compared to projected casualties based on Sicily experience. That represented roughly 200 ships and 12,000 sailors who survived because they weren't sitting stationary on hostile beaches for 45 minutes at a time. The modification also had strategic logistics impact that extended beyond combat operations. After beachheads were secured, LSTs became the primary means of delivering supplies to forward areas where ports were damaged or non-existent. The extended ramps allowed LSTs to maintain high sortie rates, unloading quickly and returning for another load. In the build-up for the invasion of Japan, cancelled after the atomic bombs ended the war, planners had calculated that LSTs with extended ramps could maintain supply flow rates 50% higher than ships using pontoon systems. Andrew Higgins never received official recognition for the extended ramp modification. There was no ceremony, no medal, no citation from the Secretary of the Navy. The Bureau of Ships directive mandating the modification didn't mention Higgins by name, referring only to improved bow ramp configurations developed through operational experience. The official Navy history of amphibious operations mentioned the extended ramps in a single footnote, attributing the development to industry cooperation with Navy requirements. This anonymity didn't surprise Higgins. He'd built his reputation and his fortune by solving problems, not by seeking credit. Higgins Industries' wartime revenue exceeded $200 million. The company employed over 25,000 workers at peak production. Higgins became wealthy and influential. Recognition from official channels was irrelevant compared to the knowledge that his modification had worked and had saved lives. But the lack of official recognition also reflected an uncomfortable truth about innovation during wartime. The military establishment, necessarily focused on following procedures and maintaining order, often resisted ideas from outside the formal chain of command. Innovations that succeeded did so despite institutional resistance, not because of institutional support. Higgins's extended ramp worked because he built it without permission, demonstrated it without authorization, and installed it on ships before the Navy could complete their review process. This pattern repeated throughout the war. The proximity fuse, which revolutionized anti-aircraft warfare, was developed by civilian scientists who bypassed military oversight to accelerate testing. The nylon parachute, which saved thousands of airmen, was adopted only after manufacturers demonstrated that silk supplies were insufficient. The diesel-electric submarine propulsion system, which made American submarines the most effective in the world, was initially rejected by Navy submariners who preferred traditional diesel engines. In each case, innovation required individuals willing to ignore regulations, risk their careers, and prove their ideas through demonstration rather than through paperwork. The system worked, but it worked inefficiently, wasting time and talent on bureaucratic obstacles that could have been eliminated with different institutional cultures. After the war, Andrew Higgins attempted to transition his company to civilian production. Higgins Industries had the capacity, the workforce, and the experience to become a major manufacturer of commercial boats and vehicles. But the transition proved more difficult than wartime production. Government contracts ended abruptly in August 1945. Orders were cancelled. The workforce, sustained by military demand, faced immediate layoffs. By 1946, Higgins Industries employed fewer than 5,000 workers. By 1948, the company was struggling financially. Higgins died in 1952, his company bankrupt, his industrial empire dissolved. The factories that had produced 20,000 landing craft sat empty or converted to other uses. The welders and engineers who had built the tools of victory dispersed to other industries. New Orleans Industrial Canal, which had hummed with wartime production, returned to peacetime shipping and commercial fishing, but the landing craft remained. Hundreds of LSTs continued service with the Navy for decades after the war. Many were sold to allied nations or converted to commercial use. Some remained in service into the 21st century, their extended bow ramps still functional, 70 years after Higgins had sketched the original design on a beach in Maryland. LST-325, the ship that had demonstrated the prototype extended ramp in June 1943, had a particularly notable post-war career. She was transferred to Greece in 1964, served in the Greek Navy as Syros until 1999, then was purchased by the USS LST Ship Memorial Organization and sailed across the Atlantic to the United States under her own power. At 60 years old, she was the oldest operational LST in existence. Today, she operates as a museum ship in Evansville, Indiana, the city where hundreds of LSTs were built during the war. Visitors can walk through LST-325's tank deck, stand at the bow where the extended ramp mechanism is still visible, and imagine what it was like to ride that ramp toward a hostile beach. The ship is maintained in operational condition, a floating reminder of the industrial mobilization that built over 1,000 such ships in less than 4 years. The extended ramp modification, now a historical footnote in amphibious warfare development, established principles that influenced military logistics for generations. The fundamental insight that reducing unloading time reduces vulnerability shaped how military planners approached contested logistics operations. Modern amphibious assault ships, while technologically sophisticated compared to World War II LSTs, still prioritize rapid vehicle discharge as a primary design requirement. The V-22 Osprey, a tiltrotor aircraft that revolutionized Marine Corps aviation, was designed specifically to reduce the time Marines spend in vulnerable transport aircraft approaching landing zones. The reduction from helicopter approach times to Osprey approach times, approximately 40%, echoes the same 40% reduction Higgins achieved with extended LST ramps. The tactical principle remains constant. Speed reduces casualties. The modular construction techniques Higgins developed for mass-producing landing craft influenced post-war industrial manufacturing across multiple industries. The concept of prefabricated components assembled on production lines became standard practice in industries, from housing to automobiles to aircraft. Kaiser Industries, which had pioneered similar techniques in Liberty ship construction, applied the lessons to post-war aluminum production and became one of America's largest industrial corporations. The welding techniques developed at Higgins Industries, particularly the lightweight tube frame construction, used in the extended ramps, found applications in aerospace and automotive manufacturing. The same engineering principles that created a ramp strong enough to support tanks, while light enough to be practical, became the foundation for aircraft fuselage designs and race car chassis construction. Perhaps most significantly, Higgins's willingness to bypass official channels and prove his concepts through demonstration influenced how military innovation was approached in subsequent conflicts. The Defense Advanced Research Projects Agency, created in 1958 inches response to the Soviet Union's launch of Sputnik, was specifically designed to allow rapid development and testing of experimental technologies outside traditional military procurement procedures. DARPA's mandate was essentially to institutionalize what Higgins had done informally, create a path for unconventional ideas to be tested and adopted quickly without bureaucratic delays. The extended ramp modification saved 12,000 lives through reduced LST casualties. That number is documented and quantifiable, but the broader impact, the cumulative effect of faster logistics on campaign timelines, the strategic flexibility that rapid ship turnaround provided, the psychological advantage of knowing that armor would arrive quickly when needed, these factors resist precise calculation, but were equally important to Allied victory. Every tank that rolled off an LST in 12 minutes instead of 45 minutes reached the battle sooner. Every LST that withdrew undamaged, because it wasn't exposed for extended periods, remained available for future missions. Every sailor who survived because his ship wasn't a stationary target went home to his family. These are the real measures of innovation's value. Historians debate the factors that determined Allied victory in World War II. Military leadership, industrial capacity, intelligence advantages, technological superiority, all contributed. But beneath these high-level factors were thousands of small innovations, many developed by obscure individuals solving specific problems. The extended LST ramp was one such innovation. Not glamorous, not celebrated, but absolutely essential to the amphibious operations that carried the war to Axis homelands. The lesson from Higgins's story is not that bureaucracy is inherently bad or that regulations should be ignored. The lesson is that rigid adherence to procedure can be as dangerous as chaos. Organizations, whether military or civilian, need mechanisms for rapid innovation when circumstances demand it. They need to listen to people who see problems clearly because they work with those problems daily. They need to distinguish between rules that ensure quality and rules that simply protect established interests. Andrew Higgins saw tanks stranded on an LST and understood immediately what was wrong. He sketched a solution in 5 minutes that Navy engineers had failed to develop in months. He built a prototype without authorization, demonstrated it without approval, and installed it on ships before the bureaucracy could respond. This was not reckless disregard for order. It was recognition that in wartime, speed matters more than paperwork. The 47 LSTs that landed at Sicily with extended ramps did so because Higgins didn't wait for permission. The thousands of vehicles that crossed those ramps in the months that followed existed because one man decided that being right was more important than following procedures. The 12,000 sailors who survived because LSTs weren't sitting targets validated Higgins's gamble that results would justify methods. In today's world, where innovation cycles accelerate and disruption affects every industry, Higgins's approach remains relevant. The next breakthrough might come from someone outside the established system. The next critical innovation might require bypassing normal channels. The next problem might be solved by a welder in a shipyard, rather than an engineer in an office. The question is whether organizations will recognize that innovation when it appears, whether they will have the courage to adopt unconventional solutions, whether they will prioritize effectiveness over procedure. The LST extended ramp proves that sometimes the most important thing you can do is ignore the bureaucracy and fix the problem. Andrew Higgins died 67 years ago. His company is gone. His factories are demolished or repurposed. His name is largely forgotten outside maritime history circles. But every time a military planner calculates logistics timelines, every time an engineer designs for rapid deployment, every time someone recognizes that speed reduces vulnerability, Higgins's legacy lives on. The extended ramp was just steel and hydraulics. But it represented something more fundamental. The understanding that war is won not just by soldiers fighting battles, but by workers solving problems. That victory belongs not just to generals making strategies, but to welders making modifications. That the difference between success and failure often comes down to someone willing to take a risk on an idea that everyone else dismissed. 12 minutes to unload 40 tanks. 12 minutes that saved 12,000 lives. 12 minutes that proved one man with a sketch and the determination to build it could change the course of history. That is Andrew Higgins's legacy. Not the boats, not the company, not the fortune he made and lost. His legacy is the proof that practical solutions from unconventional sources can matter more than elaborate plans from official channels. That seeing a problem clearly and fixing it directly beats analysis and committee review. That sometimes the fastest path to victory is the one that ignores the map entirely and cuts straight across the terrain. The tanks rolled off LST 325 inches, June 1943, because Higgins didn't wait for approval. They rolled off 1,000 LSTs for the next 2 years, because he'd proven that his way worked better. And they roll off modern amphibious ships today because the principle he demonstrated, that speed saves lives, became doctrine. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.